Yeah, the interference can be clearly observed on CDs. So if you watch a CD, look at a CD, the CD will appear colorful. So you can see bands of colors. You can see all those colors, and all that is mainly because the CD itself is not colorful. CD is not CD is colorless, but the grooves, that is what makes the interference possible. So what's happening on the grooves? A ray of light comes and hits the bottom of the groove, and another ray of light comes and hits from the top of the groove, so there will be a path difference created because of the different levels of reflections. And because there's a path difference, these will interfere in your eyes, creating interference, which means what? Constructive or destructive interference. So you will see constructive and destructive interference in your eyes. When you use white light, there will be some color that is constructive, or a set of colors will be constructive and set of colors will be destructive because they have different wavelength ranges, right? So when you are talking about a path difference, some path differences will create constructive and some path differences will create destructive for the same thickness here. And that's the reason why you see a set of colors, you don't see all the colors of the rainbow. So when you look at a CD, you'll see patches of colors and they change according to the orientation, how you hold it. So the colors coming from a CD is due to interference. If you observe a CD in a monochromatic light, which means like sodium light, yellow light, so if you or red light, suppose in this room you just put a red light on and no source of white light, keep a CD in your hands and you will see a black patch, a red patch, black patch, red patch. You don't see colors as you normally see from a CD. Okay? So the interference that's taking place is because of the multiple groups. Now, if you use red on a CD, normally red laser is actually used. But then red has got a larger wavelength, so if it is red, it's got a larger wavelength. If you use blue, blue has a smaller wavelength, which means blue will be able to see tiny, tiny differences and resolve those images. In other words, when you use blue, you will be able to have tinier grooves and information stored on it. And that is what we normally know as a Blu-ray DVD, right? So a Blu-ray DVD uses Blu-rays, blue laser. And the blue laser is good because it has got a shorter wavelength, which means you can put in more data on the same CD. Okay? Whereas on red, you cannot put too much data. Limitation is there because for this, because the wavelength is big, it cannot read tiny differences. It can only do bigger differences. So you need to have bigger grooves. Now, when all these reflections take place, there are two kinds of reflections. Just like last year, you've done something about reflection on a fixed boundary, reflection on a free boundary. Remember that? When you did waves? Reflection at a fixed boundary and a reflection at a free boundary. That same concept applies to light as well. When light goes and hits a fixed boundary or a denser medium. So this is a denser medium. And when light goes and bounces on it, after reflection, the ray will bounce this way. And so what's happening is, you can see the phase is shifting by 1/2 pi. The phase is shifting by 1/2 pi. So when reflection takes place at a denser medium, there is a phase change. So there is a change in phase of pi radians, and the same way a change in path of lambda. over 2. This is something that takes place when a reflection takes place at a dense medium. So when a wave goes like that and bounces back on a dense medium, a phase change of pi automatically takes place and a path change of lambda over 2 automatically takes place because it's a denser medium. You understand this? Phase change of pi and all. See, for one full wave, what is the total phase? 2 pi. And that corresponds to lambda. So a complete phase of 2 pi corresponds to a path of lambda. So when it suffers a phase change of pi, it is equivalent to a path change of lambda over 2. Make sense? Try to get that idea. Now what happens when the waves go and hit a rarer medium? That means this side is denser. If it's going to hit a rarer medium, then the waves will not suffer a phase change. So when this goes like this, after reflection, it will come back the same way. No phase change. So no change in phase, no path difference produced. No phase change and no path change. No phase change and no path change in this case. Okay. So when reflection of light takes place at a dense medium, automatically a change of phase is going to take place like this, and a path changes this way. It is already created. When a reflection takes place at a rare medium, no phase change or path difference is created. Okay? Now in the case of a CD, the first reflection is taking place from the top, which is a dense medium. The second one is also taking place from the top of the dense medium. So these two don't suffer any phase change. And so if these two meet with a path difference of 0 or lambda or 2 lambda or 3 lambda, then it's going to be constructive. Now this is for path difference, delta. If the path difference is, so the path difference, for path difference of 0, lambda, 2 lambda, 3 lambda, it's going to be constructive. For path differences of lambda over 2, 3 lambda over 2, 5 lambda over 2, etc., is going to be destructive. So the conditions for interference, this is the condition for interference. If the path difference is 0, lambda, 2 lambda, 3 lambda, constructive. If the path difference is lambda over 2, 3 lambda over 2, and all the odd multiples of lambda over 2, then you get destructive interference. So basically the condition for constructive is n lambda. Where the n is a whole number. Condition for destructive is n plus 1 lambda over 2. Condition for destructive is n plus 1 lambda over 2. Put whole numbers for n. When n is 0, that one. When n is 1, 2, 3. Now for destructive, when n is 0, it's lambda over 2. When n is 1, oh no, these are supposed to be odd. Oh, 2n, sorry. 2n plus 1. 2n plus 1 lambda over 2. So when n is 0, this one. When n is 1, it will be 3 lambda over 2. When n is 2, it's going to be 5 lambda over 2. Okay, get it? So this is the condition for destructive interference to take place, path difference, and this is the path difference required for constructive interference to take place. Now this is in terms of path. In terms of phase, it's going to be in terms of pi. So if you're going to talk about phases, it won't be in terms of lambda, it will be in terms of pi. So when you look at a light shining on a CD, if you're seeing a particular color in it, that's because it is constructive. It may be any of these conditions, but it's constructive. If you're missing a particular color, that's because those colors fell into the interference, destructive interference area. Get it? So what are the conditions for interference? There is a condition for interference. Conditions for interference. Now what happens? Oil on road. Oil on road is like this. This is the road. The oil drops somewhere, and then the oil kind of spreads off to both sides. So where it dropped, it's going to be thicker, and where it is spreading off, it's going to be thinner and thinner, right? So what happens is here, when light comes and falls, on it, the light reflects off first, this way. Where is it getting reflected off? On a dense medium or rare medium? On a dense, because it's going from air to, it's going from air to the oil. Therefore, it is hitting the denser medium. It's hitting the denser medium. Because it's hitting the denser medium, there is already a lambda over 2 created, or a pi created. It's already creating a path difference. Its phase is changed by pi. What happens to the other one? The other one goes in to the bottom of the oil. And what's below that oil? The gravel, but before that is air. So it's basically trapping a layer of air between, right? So what happens is this one is going to hit on a rarer medium. It's going to hit a rarer medium. And so it suffers nothing, no change. So this one suffers a lambda over 2. This one suffers nothing. So both of these already have a lambda over 2. Now, if this thickness of this oil going down and coming back, if that entire distance is another lambda over 2, if this distance from here to here and back up to the top, if that is lambda over 2, then what is the total path difference created? If this is suffering already a lambda over 2, this is already suffering a lambda over 2, so basically there won't be a path difference. There won't be a path difference. Because this already suffered a path difference of lambda over 2 because of reflection. The second one did not suffer a path difference because of reflection, but it suffered because it was already going down and up. Make sense? And so overall, both of them suffered equally, so it should be constructive, right? Because it falls in this category then. So this will be constructive. Even though there is a path difference of lambda over 2, it is constructive. Now, what if you look at something here, a ray that goes and hits here? Yeah, this suffers lambda over 2. And what if the total path from here to here and from here to here is a lambda? Then this is lambda over 2 and this suffers a lambda. So now the path difference is lambda over 2. So what is supposed to be the kind of interference? Destructive. Destructive. So what happens is the light that comes and hits here if it coincides with the correct path differences and all that, if it satisfies the condition for constructive, you will see it constructive. You will see that particular color. The light comes and hits here, and if that same color satisfies the condition for destructive interference, you will not see that color there. So why that color is missing from there is because it falls in the diffraction, destructive interference area. Make sense? So when you look at an oil patch, you see not all the colors. You don't see the rainbow of colors. You'll see like one patch of color, and then another patch, another patch, another patch. It won't be uniform. So the condition for interference is like this. It's totally different. And this same thickness is going to be happening all around, right? So if you keep tracking, so looking at it from above, this is how the oil drop is spreading. So that same path difference must be available all around somewhere. That's why you see those colors are always kind of complete loops. Why are they not kind of really circles? Why are they not perfect circles? Because why are they not perfect circles?
The oil spreads out.
Because the way it spreads is not even. Because it's a road. How the oil spreads is not even. And especially if there is a little water flowing also along with it, then it will kind of drag it one way. So the thickness is not even everywhere. So you will end up seeing patches like, and then this. The pattern that you see is not uniform. Why it is not uniform is because the way it is spreading out is not uniform. Get it? Soap bubbles. What is happening in a soap bubble? On a soap bubble, this is, have you seen colors on a soap bubble? Have you seen colors on a soap bubble? Yeah. So how is the color taking place on a soap bubble? Watch. If a ray of light comes and hits here, you'll get the first reflection from there. Is it hitting a denser medium or a rarer medium?
Yes.
And therefore this suffers a lambda O2 path difference, right? Because that's soap and that is air, it's going to suffer a lambda O2. What will happen to some of the remaining part? It goes refracting and it hits here and it bounces back and then comes off. Now the second one is hitting what medium? Air, because inside the soap bubble it is air. So the first one hits the soap solution, the second one hits the air boundary. And so there is no path difference for this. So just like an oil drop, this also has the same concept, same thing. So if this path difference is lambda over 2, then they will both be interfering constructively. If the path difference here, the physical path difference, if it is a lambda, if the physical path difference is a lambda, then adding this to it, it will be destructive. Make sense? So the conditions are completely reversed. These will be for constructive and these will be for destructive because of this extra thing that's coming up. Making sense? Right? Now, again, in the case of soap bubble, why are the colors not like fixed? Why are they not staying still?
Bubbles thicker in different spots.
Exactly, and plus gravity pulls it down. Because it's gravitational force acting on it, the bubble will actually like lose its liquid here and starts piling up here. So the bubble actually becomes thicker at the bottom and thinner and thinner and thinner at the top. It becomes thinner and thinner at the top. So as the thickness changes, colors change. So why are the colors changing on the soap bubble is because thickness is changing. So as the thickness changes, different colors satisfy the condition for constructive. And so the colors change. Make sense? Right? Write it down. Now, just before the bubble breaks, the thickness is nearly 0. the thickness is nearly zero. And when the thickness is nearly zero, for all colors, only this exists. Because the physical path is not existing. Make sense? When the bubble is about to break, it becomes so thin that the physical path is hardly there. And what is there? This. And that satisfies what condition? So what will you see? Like none of the colors are constructive. It's all destructive. So what do you end up seeing? You see some gray patches. Have you seen gray patches on a bubble that is about to break? When a bubble is about to break, you can tell it's going to pop. Just look at the gray patches. The moment gray patches appear, you know it's going to break. Why gray patches? Because when you start seeing gray patches, the thickness becomes so small that physical path difference is nearly zero. That means the only path difference that is seen is because of the reflection, and that is lambda over 2. And that is for destructive. Destructive for all colors, literally. So when all colors are destructive, you don't see anything but a patch, a black patch or gray patch. Next time you blow a bubble, wait for it to pop. Just before popping, you can see shades of gray appearing. The moment shades of gray appear, that means it's ready to pop. Check it out, okay? Something you should be able to try. If you can blow a bubble from some soap solution, blow the bubble and keep watching. Colors change, colors change, colors change. The moment it becomes gray patches, time to break. It will break. You can try that. So, yeah, so bubbles, why they're colorful? Newton's rings. Well, Newton poked his nose even here in optics. He has done a lot of contributions in different areas, but this is something that he has found out. What is a Newton's ring? Newton's ring is just like the oil drop. What he did was he placed a glass block and a lens on top. So when he keeps the lens on top like this, can you see that shape? So when the glass, so that's a glass, and I'm just zooming it in. This is the glass, and this is the lens. That's a lens. Now the best thing to have is a plain lens like this. But we can also see with this lens. So when the lens makes a contact with an optically plane glass plate, which is not this. I don't have the setup here for demonstrating it, but this is what it is. Now when a light comes and hits here, this light goes down here and gets reflected. And then the next part of it goes down, gets reflected. Where's the first one getting reflected? At a dense medium or rare medium? The first one is hitting here, which is the air, because this is air. In the wedge, you see air. So the first one is reflecting at the bottom of the lens, which is basically at the air. So this suffers nothing. Look at the second one. Goes down, hits the other block, comes back. So there it suffers a lambda over 2. That one suffers a lambda over 2. Right? So when this suffers a lambda over 2, again, just like how we discussed about the oil film, the same way. If this path is another lambda over 2 or 3 lambda over 2 or 5 lambda over 2, the overall interference is going to be positive, constructive. If this path difference here, the physical path difference is 0 or lambda or 2 lambda or 3 lambda, it's going to be, adding this one to it, it's going to be destructive. Is that clear? Now, when you keep a lens like this, isn't the gap very uniform, unlike the oil film? It's very uniform. So what do you expect to see then? If you're going to see one particular color interfering constructively here, it must be interfering everywhere, right? All around. So this is the block, and this is your lens. You're going to see rings. Now what are you seeing in the middle? What will you see here, right there? What's the physical path? 0. The physical path is 0, but it already has a path difference of lambda over 2. So what is expected to be seen at the middle? Black. So you will see black color like this. So you'll see black, color, 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 color. You'll see rings like this. And this, of course, can be only seen using a microscope. So are the Newton's rings right now existing? Yes, but it is difficult to see with the naked eye. It is very difficult to see with the naked eye. What we need to do is this. What we actually have to do practically is this. To observe this, we use a glass plate like this at 45-degree angle, put a light source here, and this light source hits this glass, goes down, undergoes interference, and then it comes back again through the glass. It goes to the microscope, and you'll be able to see in the microscope clear Newton's rings. Why don't you take your phones right now and look up Newton's rings? That's a Newton's ring. You can see the center of the ring is black because the center has got a physical path of 0, and therefore the only path difference created is because of the dense medium, rare medium reflection, and that's what you end up seeing. Okay. So the center is going to be black and the others. Now if you're going to watch the same thing in transmitted light, which is transmitted light means going from the bottom. If the light is going from the bottom and then coming through here, that will show you the other way around. The center will be white and then the other ones changes. But the other thing you can notice there is in the here the rings are far away, but as it goes further and further away they get crowded. Can you see the crowding as it goes away? It's getting more and more crowded because the curvature here is less. That means you can see the change of the path is going to be very gradual in this region. But as it starts curving more and more, the change of path becomes rapid. So even by a little movement, you'll be satisfying the condition once again. But here, you have to move from here to here a lot. Make sense? So these are called the Newton's rings. Now, if you use monochromatic light, that's what they have used. The yellow color that you see there is because they use sodium light. Yeah.
Does the lens have to be a perfect circle?
It has to have an optic center right there.
Okay.
I mean, even if it is kind of broken here and here, it's fine. I mean, we need this section only.
Okay.
We really don't need this part. We just need only here. Because Newton's rings are only visible in this region. You will not be able to see here because the gap is too much that the intensity changes a lot. When the intensity changes a lot, constructive and destructive cannot take place properly. You understand? For constructive and destructive interference to take place, the most important thing is the amplitudes of the waves must be identical almost. So if the amplitudes are not identical, you will not be able to see it. Constructive and destructive interference will be seen more right at the place where it is getting reflected. So over here you will be able to see it much better. Over here it becomes faint, faint, faint. Finally you won't see it at all. So even in those pictures that you see, the further away you look at it, the resolution of the picture is kind of fading off. It becomes weaker. And this side weaker. Well, that's called, yeah.
This one has like the glare in the middle. Would that happen?
That's transmitted light. Yeah, this is transmitted light. Light goes from underneath. So when light is going from above, like as I've shown here, light goes from above, then you'll see the central one as central one will be black. But if you're going to look at the same thing from here, then it'll be dark. So if you look at it by transmitted light, but first of all, the lens and this one, they're not clear. Look at a lot of the scratches. If I try to use a microscope to observe it, I'll see these scratches more than the Newton's rings. It should be optically plane. We need clean glass plate and a clean lens. If you have that, then you should be able to see the interference. I will see if I can set it up, okay? Because they need a microscope, which is like vertical. All the biological microscopes are all like at an angle. So setting it up is kind of hard. We need what is known as a traveling microscope, a microscope that can go up and down, sideways like this, and forward and backward. All 3D movements. It can slide sideways, it can go forward and backward, and go up and down. So that is what is needed, because then we can focus it properly to the Newton's rings. Now those microscopes, they can go up and down, but to move it sideways and all that is, I don't think they move. Bird feathers. Why are the bird feathers kind of colorful? It's because of interference again. Bird feathers are colorful because of interference. Peacock. Look at the beautiful feathers. All that is mainly because of the texture of their feather that creates the little path differences and gives you the. And again, what's the size of those grooves on the feathers? That will define what colors you're going to see. Now, if you observe a peacock under sodium light, which is yellow light, you won't see any of those colors. It'll be yellow-black. That's it. Shades of yellow and black. So yeah, light is a very important thing. So sunlight, when will a peacock be very colorful is only when the sun is out. When it's a gloomy day and there's hardly any sunlight, you will see the peacock's colors are not very prominent. More shine is only when the sunlight pops up. All right, so bird feathers and so many other places. Wherever you see colors, you can just say, all right, that is some interference idea, some interference concept. Even on a calculator screen, show me that calculator. Not that one, this one. Because here I can touch the screen, it says that one has got a glass. This one, if I turn it on, and if I touch the screen, you can see some colored patches. Can you see colors? Can you see that? And those colors are actually coming out because of interference. And of course, a different phenomena I'm going to talk about. There's a different phenomenon we're going to talk about. Good. So interference takes place in all these places, and have an idea about that. Next thing is polarization. 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 Suppose I create a tiny slot, let's say on the door. If I create a tiny slot on the door, like this. That's too much. Okay, if I create a tiny slot on the door like this, and if I take a rope, pass the rope through it, and if I take the rope in my hands and go up and down creating waves, transverse waves. So if I create waves like this, what will happen? Will they pass through to the other side? I'm moving the rope up and down, and the slot is vertical. It will pass through. It will pass through. So this will pass through straight away. But if I keep the same thing sideways, if I keep the slot like this, sideways, and then send the waves, if I send these waves, what do you think is going to happen? Yeah, it will just, it can bounce back or it just blocks. So, because the door is already, slot is vertical, If I take the rope and go sideways, will these waves go through? They won't. Because the door has the freedom to let the vertical transverse waves to go through, but not the horizontal. So if I do horizontal waves into it, the horizontal ones won't pass through. So these are going to be blocked. And this action that you see here is called polarization. What is polarization? Restriction of transverse waves to a single plane. Restriction of transverse wave to a single plane. That's called polarization. Restriction of transverse waves to a single plane. So, for instance, if I have that slot, suppose I have that slot, and if I take the rope and if I go crazy, all directions, I create waves in all directions. I make vertical waves, I make horizontal waves, I make all sorts of waves in all directions. If I send all the waves of all directions into it, what will happen? Only the vertical ones will pass through. That is polarization. Restriction of transverse waves from many different planes to a single plane. Restriction of transverse waves from many different planes to a single plane is called polarization. And this gadget is called a polarizer. This gadget is called a polarizer. How do you know this is polarized? You can just keep one more like this. There. You can keep one more in the horizontal manner, and what will happen? It won't go through. You get it? This is called polarization. Why is sound not polarizable?
It's not transverse.
It is not transverse. Good. It is longitudinal. So if I create sound, sound will go through that gap. Because sound is longitudinal, not transverse. So in other words, light was proved to be transverse through polarization of light. Now, can that gap polarize light? Can that physical gap of this much polarize light? No way. Why? Because the wavelength of light is very small, and that gap is too big. Because the gap is too big, nothing is going to block it. You need very fine gaps if you want to really block it. In other words, like a diffraction grating, you need fine slots. If you can have fine slots, then you can polarize light. If you have fine slots, some slots that you don't even see with your eyes, then you can polarize light. Microwaves, the wavelength of microwave is like millimeters to centimeters. So a grill like that can polarize microwaves. My fingers can polarize microwaves. I've done that here. Now the gadget is not working properly, so I can't demonstrate it. I have a microwave transmitter and a microwave receiver. And the microwave receiver is connected to a sound detectors or sound producing gadget. So when the microwaves are turned on, it is it's polarized in one plane only. So the microwave that's coming here is one plane, the vertical plane. and the receiver picks it up and creates a noise, right? What I used to do is I use my fingers. I go vertically down like this. When I go vertically down, microwaves still pass through, no problems, and the sound is still there. When I rotate my hand like this, blocks. So microwaves are blocked when I keep my hands like this, and microwaves are going through when I keep my hands vertical. Yeah.
So is that like the sheath and the microwave? Is that
There we go.
what it does?
That is exactly right. You know, on the microwave door, you have seen the net sort of thing. Why they keep it a net, not like only one way, is because microwaves are bouncing everywhere internally. So when they bounce, they may change their orientation. When they change their orientations, you cannot always expect one way. They can be any way. So the best thing to do is put a grill like this, put another grill like this, guaranteed you're cutting everything. That's why you have the wire net thing. So that wire net will allow light to come through, so you can see the food that is getting cooked, but microwaves don't come out. It's microwaves inside. So it's dangerous. So suppose an inexperienced technician or a do-it-yourself kind of guy, he does not know about the theory behind the door, the net, and all those things. So suppose by some chance the door broke, he'll say, all right, I can fix it. Put a piece of glass over there, touch it. So if you just replace it with a piece of glass, guess what? When you cook food, the microwaves are going to come out. So if you're going to watch it, you are affected by it. It will come out. So that's why the door is of that same shape. And when you open the microwave door, the microwave has to turn off because there's a switch right there. You know, you can see the door is actually like having kind of levers, and they push into the hole and turn the thing on. So once it is out, it has to turn off, just to protect, because you don't want that thing to operate while it is open. Well, you can operate it. There are ways to get it operated by keeping the door open, but who wants to do it, right? So automatic cutoff is already there. So microwave is not going to work if the door is not closed. Now, if the switch gets faulty, then even with the door closed, it won't operate. Okay? It happened to me once. I made a mistake. I called the warranty people, the home warranty. I thought they were covering it up. So therefore, when I called them, made an appointment, they came, inspected, and they said, oh, this is the older model of microwave, so we can't, this is not covered. And I paid $90 for his visit, just to tell me that it cannot be covered. And then I said, okay, now $90 wasted. Now let me see what can be done. And I opened the panel, and I found out that this particular micro switch is faulty, $3. Got it on eBay, put it up there, it was working. I could have done that before myself. I just thought, okay, maybe a new microwave, a little selfish there. Instead of like thinking of repairing it, I just went the other way around thinking, okay, maybe we can get a new microwave because we have warranty. But the other part is hidden, anybody comes and checks, you have to pay money for them. $90 for his visit, that's a lot. He didn't stay for 5 minutes also. All right, so this is the polarizer. So what's the job of polarizer? So for polarizing microwaves, you need a polarizer which is like so fine. And this is the polarizer. The light that's coming through is polarized light. So when I look like that, the light that's coming from there to my eyes is already plain polarized. It's like this. This light that's coming from there is ordinary light, this way. Sunlight and all the lights are ordinary. This is called ordinary light. Ordinary light means in all planes. But this will polarize it to a single plane. Now, how do you know that this is polarized light? Put another one there. Can you see through it? That's because the first one is vertical, the second one is also vertical. That's why you're able to see it. What if I turn one of them, any one of them, through 90 degrees? In other words, I make it this way. You won't be able to see anything at all. See, I'm turning it through 90 degrees. I cannot see you. Yeah, I cannot see you. It's pitch black. I'll send it to you. So just pitch black, it's completely blocked. I can barely see the tube lights, a little bit. And this is a good thing to observe solar eclipse. In fact, last year was it?
Yeah.
When the solar eclipse came, I just used this. I went outside and used this one. It was crystal clear. I didn't use the other glass. I used this one, so it's very clear. Yeah, this is called cross polarites. If I turn it once again, 90 degrees, it's transparent again. See? You can see the change in intensity. The brightness changes. It depends on how it's oriented. When the maximum is coming out, that means it is. So that's called polarization. Now these are the Polaroids. Cutting light. Polarization. So you understand the concept of polarization. Where are these used?
Sunglasses.
Sunglasses. Good. What kind of sunglasses are you talking about? Which kind of sunglasses? Is it the day and night glasses you're talking about? Is that day and night? No? You know the day and night type? Transition types? Like when you're in these rooms or darker areas, they will be transparent very clearly. But when you go out in sunlight, it just changes to dark. And how is that happening is because they have exactly the same concept, but it is more on the molecular level. So the molecules are actually like this. There are two layers. When light shines, these molecules will twist to the right, and that also twists to the right, like this. So the more and more they twist, the lesser light passes through. So it becomes dark. And it's activated by light. So sunlight creates the big difference there. So when sunlight falls on it, this twisting of molecules makes the lattice spaces. So basically the lattice space is acting as a Polaroid. Right? Where else have you seen this? Now the sunglasses you're talking about is a different one. So I'll explain to you that part of it. Polarization by reflection. Polarization by reflection. Suppose you have glass here. Suppose you have glass. Suppose you have glass, and this is ordinary light coming and hitting. That's ordinary light coming and hitting there. Ordinary light. Why is it ordinary? Because it has all the planes. All the planes. But I'm primarily showing only two planes. The vertical and the horizontal. The vertical and the horizontal. The vertical and the horizontal. I'm only showing two of them. So when this ordinary light comes and hits glass, what happens here? Some of it reflects. Some of it reflects, right? And some of it refracts. Some of it reflects and some of it refracts. Tell me which one has a greater chance of getting reflected, the vertical or the horizontal? Think of, okay, that's glass, that's the vertical, that's the horizontal. Which one has a more chance of reflecting? The vertical or the horizontal? Horizontal. That's right. Think of this, you're standing next to a pond and you have a slab of glass, a slab of stone, and you are opting to throw it this way and this way. Which has a greater chance of bouncing? Horizontal. Have you done skipping? Yeah. So this way it bounces. This one has a greater chance of going in. So what happens is, in the reflected light, more of the horizontal will be seen, and occasionally that. In the refracted light, more of these are seen, and occasionally that. So this is partially polarized. And this is also partially polarized. Both are partially polarized. If this angle of incidence is I, this angle is also going to be I. And this angle of refraction R. When will you get maximum partially polarized reflection? Is when this angle is 90 degrees. That's when you get maximum, because between horizontal and vertical it is 90 degrees. So when this angle between the reflected light and the refracted light is 90 degrees, you get maximum. So what is the, if this is I, what is R? And you know refractive index N is equal to sine I over sine R, Snell's law. So sine I over R is 90 minus I, correct? Sine 90 minus I. And you're good at trigonometry, so you know sine 90 minus I is cosine I. You know it? I'll show you how it is later on. Sine 90 minus I is cosine I. So what you end up getting there is the refractive index is tan I. So the angle of this is called polarizing angle. IP is called the polarizing angle. And what is IP? It's the angle of incidence for maximum percentage polarization. For maximum percentage polarization. It's always like for 1.5 for glass, this should be somewhere in the 50s. Now, is this something that you can find? You can see it. Can you see the glare coming on the floor? I want you to test it out right now. You can observe, using this one, observe the glare coming from the floor, and you see that the glare is cutting off.